Hello, welcome to our CompTIA Security Plus course. In this lesson, we're going to talk about the different PKI components. So to begin to understand the applications and deployment of a public key infrastructure or PKI, right, you should understand the various pieces that make up a PKI. A PKI is a vast collection of varying technologies and policies for the creation and use of digital certificates. A PKI encompasses certificate authorities, digital certificates, and a variety of tools, systems, and processes. As from the previous lesson show, digital certificates are a critical component in providing secure systems. For example, many implementations of EAP in wireless networks require digital certificates to verify the identity of the client or server. Digital signatures are digitally signed data blocks, and they provide several potential functions, but most notably are used for identification and authentication purposes. The requirement for certificates adds complexity. Now, the basic concepts of public and private keys plays an important role in PKI. This infrastructure makes use of both types of keys and lays a foundation for binding keys to an identity via a certificate authority or CA. Right? CA. This gives the system a way to securely exchange data over a network using an asymmetric key system. For the most part, this system consists of digital certificates and the CAs that issue the certificates. The certificates identify individuals, systems, and organizations that have been verified as authentic and trustworthy. Now, recall that symmetric key cryptography requires a key to be shared, right? For example, suppose the password to get into the clubhouse is open sesame. At some point in time, this key or password needs to be communicated to other participating parties before it can be implemented. PKI provides confidentiality, integrity, and authentication by overcoming these challenges. With PKI, it is not necessary to exchange the password, key, or secret information in advance. This is useful when involved parties have no prior contact or when exchanging a secure key is neither feasible nor secure. PKI is widely used to provide secure infrastructure for applications and networks, including access control, resources from web browsers, and secure email. Now, PKI protects information by providing the following. It can provide identity authentication. It provides integrity verification. It provides privacy assurance, access authorization, transaction authorization, and non-repudiation support. So a public infrastructure consists of technologies and policies for the creation and use of digital certificates. Let's first talk about the CA, or Certificate Authority. CAs are trusted entities and an important concept related to PKI. An organization can use third-party CAs, and it can also establish its own CA, typically for use only within the organization. A CA's job is to issue certificates, verify the holder of a digital certificate, and ensure that holders of certificates are who they claim to be. A common analogy for a CA is a passport issuing authority. To obtain a password, right, you need the assistance of someone, for example, a customs office, to verify your identity. Passports are trusted because the issuing authority is also trusted. Registration authorities, or RAs, right, provide authentication to the CA on the validity of a client certificate request. In addition, an RA serves as an aggregator of information. For example, a user contacts an RA, which then verifies the user's identity before issuing the request of the CA to go ahead and issue a digital certificate. A CA is responsible for issuing certificates. Remember that an RA initially verifies a user identity and then passes along to the CA, okay, with a request to issue a certificate to the user. CAs follow a chain hierarchy or certificate chain when verifying digital certificates to form what's known as a chain of trust. Starting with a trust anchor known as the root CA, certificates are trusted transitively through one or many certificates within the chain. Here is an example of certificate chaining. First, the root certificate verifies certificate A, right? So you have the root. So it verifies certificate A. Then certificate A verifies certificate B. Then certificate B verifies certificate C. Okay, this can also work in reverse, like certificate C references certificate B, B references certificate A, then A references the root certificate. Okay, now let's talk about certification practice statement. A certification practice statement, or what we call a CPS, is a legal document that the CA creates and publishes for the purpose of conveying information to those who depend on the CA's issued certificate. The information within the CPS provides for the general practices the CA follows in issuing certificates and customer-related information about certificates, responsibilities, and problem management. It is also important to understand that these statements are described in the context of operating procedures and system architecture. Certificate policies, on the other hand, indicate the rules that apply to an issued certificate. A CPS includes the following items: identification of the CA, types of certificates issued and applicable certificate policies, operating procedures for issuing, renewing, and revoking certificates, and technical and physical security controls that the CA uses. Now, what are trust models? Certificate authorities in a PKI follow several trust models or architectures. The simplest model is the single CA architecture, in which only one CA exists to issue and maintain certificates. This model might benefit small organizations because of its administrative simplicity, but it can represent many problems. For example, if the CA fails, no other CA can quickly take its place. Another problem can arise if the private key of the CA becomes compromised. In this scenario, all the issued certificates from the CA would be invalid. A new CA would have to be created, and the new CA would need to be reissued with all the certificates. A common model, and one that reduces the risks inherent with a single CA, is the hierarchical CA trust model. Right, so let me put, like earlier we spoke about single, and now we have hierarchical. Okay, so in this model, an initial root CA exists at the top of the hierarchy, and subordinate CAs or intermediate CAs reside beneath the root. The subordinate CAs provide redundancy and load balancing in the event that any of the other CAs fail or need to be taken offline. Because of this model, you might hear PKI referred to as a trust hierarchy. An intermediate CA has a certificate that is issued by the trusted certificate. This certificate is issued so that the intermediate CA can issue certificates for others. This results in a trust chain that begins at the trusted root CA, and it goes through the intermediate and ends with the SSL certificate issued to a server with which you are interacting. A root CA, like this one, right, differs from the subordinate CAs in that the root CA is usually offline. Okay, remember that if the root CA is compromised, the entire architecture is also going to be compromised. If a subordinate CA is compromised, however, the root CA can revoke the subordinate CA, such as this one. Okay. Now, what is a key escrow? Key escrow occurs when a CA or another entity maintains a copy of the private key associated with a public key signed by the CA. This scenario allows the CA or escrow agent to have access to all information encrypted using the public key from a user certificate and to create digital signatures on behalf of the user. Therefore, key escrow is a sensitive topic in the PKI community. Harmful results may occur if the private key is misused. Because of this issue, key escrow is not a favored PKI solution. Now, despite public concerns about escrow for private use, key escrow is often considered a good idea in corporate PKI environments. In most cases, an employee of an organization is bound by the information security policies of that organization. In addition, key escrow enables an organization to overcome the large problem of forgotten passwords. Instead of revoking and reissuing new keys, An organization can generate a new certificate using the private key stored in escrow. Key escrow is used for third-party custody of a private key. Let's talk about digital certificates. So here, a digital certificate is a digitally signed block of data that allows public key cryptography to be used for identification purposes. The most common types of certificates are the SSL or TLS certificates, right? I'll put it here, or TLS certificates used on the web. Essentially, these certificates ensure communications which occur when a website uses like HTTPS and / instead of just HTTP and the browser address bar accompanied by a closed padlock. CA issued these certificates which are signed using the CA's private key. Most certificates are based on the X.509 standards, although most certificates follow the X.509 version 3 hierarchy PKI standard. The PGP key system uses its own certificate format. Now, you likely have used the most common application of digital certificates. Websites that ask for personal information, especially credit card information, uses digital certificates. The traffic from your computer to the website is secured using SSL TLS, right? And the web server uses a digital certificate for the secure exchange of information as indicated by a small padlock located in the status bar or address bar of most browsers. By clicking this icon, you can view the digital certificate and its details. Public and private key usage. So here, digital certificates and key pairs can be used for various purposes, including privacy and authentication. The security policy of an organization that is issuing a key or the CA defines the purposes and capabilities for the certificates issued. To achieve privacy, users need the public key of an individual or entity that they want to communicate with securely. This public key is used to encrypt the data that is transmitted, and the corresponding private key is used on the other end to decrypt the message. You can obtain another's public key, right, which is freely available to anyone and use it to encrypt a message to that person. As a result, the person can use his or her private key, which no one else has, to decrypt the message. The public and private keys are mathematically related. Authentication is achieved by digitally signing the message being transmitted. Now, to digitally sign a message, the signing entity requires access to the private key. Now, what is a certificate signing request or a CSR? Now, to install a digital certificate, a specific request needs to be generated and submitted to the CA. The applicant applies to the CA for a digital certificate known as the CSR. Included within the request is the applicant's public key, along with the information about the applicant, such as the following, like the FQDN or the fully qualified domain name, the legally incorporated name of the company, department name, city, state, and country, and the email address. Now, before submitting a CSR, the applicant generates a key pair consisting of a public key and a private key. The public key is provided with the request, and the applicant signs the request with a private key. If all is successful, the CA returns a digital certificate that is signed with the CA's private key. Next is certificate policy. A certificate policy indicates specific uses applied to a digital certificate on the other technical details. Not all certificates are created equal, right? Digital certificates that are issued often follow different practices and procedures and are issued for different purposes. The certificate policy provides the rules that indicate the purpose and use of an assigned digital certificate. For example, one certificate might have a policy indicating its use for electronic data interchange to conduct e-commerce or areas. Another certificate might be used to digitally sign documents. Remember that a certificate policy identifies the purpose for which a certificate can be used. In addition, other types of information can be included within the certificate policy, such as legal issues often used to protect the CA, mechanisms for how the CA will authenticate users, key management requirements, instructions for what to do if the private key is compromised, lifetime of the certificate, certificate enrollment and renewal, rules regarding exporting the private key, and private and public key minimum lengths. the applicant's public key is submitted along with the CSR. Okay. Now let's talk about certificate types. Three types of validated CLS certificates exist, each with its own level of trust. The first one is domain validation. This type of certificate includes only the domain name. DV certificates can easily be issued, just as the domain name lookup can easily be performed against WHOIS, which is a database of registered domains. Domain validation or DV certificates are inexpensive and can be acquired quickly, so if trust is important or if a public-facing website is desired, organizations should consider another type of validated certificate. Next is organizational validation, or OV. Right? This certificate type provides stronger assurance that the DV certificate, as organizations are vetted against official government sources. The OV certificate is therefore a common certificate type for many public-facing websites. Unlike with the DV certificate, OV certificate verification requires a more manual review and verification process, and this can take days to process. And the third one is extended validation, or EV. This certificate type provides a high level of trust and security features. EV certificates are easily identified as the business name in the address bar screen. EV certificates are designed to provide assurance against phishing attacks. Now, as the name implies, this certificate type requires a comprehensive validation of the business, which can take up to a couple of weeks to acquire. So again, right, the summary, DV are the quickest and the least expensive certificates to acquire. EV can take a couple of weeks and are the most expensive, but they also provide the highest level of trust. Now let's talk about certificate formats. Certificates can have various file extension types. Some but not all extension types are interchangeable. Now be sure to determine whether a certificate is binary or base64 ASCII encoded. The most common format and extension for certificates is the PEM format, or what we call as the Privacy Enhanced Mail, which is mostly associated with Apache web servers. The PEM format is a base64 ASCII encoded text file, which makes copying the content from one document to another very simple. A PEM file might contain several certificates and private keys within a single file, although having each component as its own file is common. A single certificate includes the header, right, or begin certificate, preceded and followed by 5 dashes, and the footer end certificate, preceded and followed by 5 dashes. A single private key includes the header begin encrypted private key, preceded and followed by 5 dashes, and the footer end decrypted private key, preceded and followed by 5 dashes. In addition to the PEM file, extension.crt, .cer, and .p7c file extensions can be used. However, the .key, right? Let me put key. Sorry, this is not p7c .key, right? This is typically used when the file contains only the private key. Okay. Now, the binary form of a PEM certificate is distinguished encoding rules, or DER, or DER certificate. In addition to the .DER extension, CER and CRT extension can be used for DER encoded certificates. DER encoded certificates are common on Java platform. Another binary certificate is PFX, if you have heard it, right? PFX, sorry. Which is also known as the PKCS 12. Extensions for the PFX, or Personal Information Exchange encoded certificates, include PFX and P12. This type of certificate is common to the Windows operating system for importing and exporting certificates and private keys. PFX supports a private key, and one or more certificates can be stored within a single binary file. DER and PFX certificates are binary encoded and cannot be edited with a plain text editor, as the base64 ASCII encoded PEM and P7b certificates can. Okay, now let's talk about certificate revocation. So digital certificates can be revoked. Revoking a certificate invalidates a certificate before its expiration date. A digital certificate contains a field indicating the date until which the certificate is valid. This date is mandatory, and the validity period can vary from a short period of time up to several years. Revocation can occur for several reasons. For example, a private key might become compromised. The private key might be lost, or the identifying credentials might no longer be valid. Other reasons for revocation include fraudulently obtained certificates or a change in the holder status, which could indicate less trustworthiness. Revoking a certificate is just not enough. The community that trusts this certificate must be notified that the certificate is no longer valid. This is accomplished via either of the following mechanism. First is a CRL, or Certificate Revocation List, which is actually a mechanism for distributing certificate revocation information. A CRL is used when verification of the digital certificate takes place to ensure the validity of the digital certificate. A limitation of CRLs is that they must be constantly updated at least every 2 weeks. Otherwise, certificates might be accepted despite having been recently revoked. Next is OCSP, or Online Certificate Status Protocol, which is kind of a newer mechanism for identifying revoked certificates. OCSP checks certificate status in real time online instead of relying on the end user to have a current copy of the CRL. Now, both OCSP and CRLs are used to verify the status of a certificate, right? 3 basic status levels exist in most PKI solutions. They are called valid, let me put it here, valid, suspended, and revoked. Okay, you can check the status of a certificate by going to the CA that issued the certificate or to an agreed upon directory server that maintains a database indicating the status level for the set of certificates. In most cases, however, the application such as web browser has a function available that initiates a check for certificates. Now, when a certificate has expired, the client is likely to receive an error message saying that the website cannot be trusted. In some situations, users may not have correct root certificates installed into their web browsers. Now let's talk about OCSP stapling. Although OCSP provides a real-time status checking, it requires the CA to respond to every client request to validate a site certificate. High-traffic websites burden the CA with this request because they need to respond to a potentially overwhelming number of certificate validity requests. A mechanism known as OCSP stapling helps reduce this load by allowing the web server to instead staple a timestamped OCSP response as part of the TLS handshake with the client. The web server is then responsible for handling OCSP requests. OCSP stapling provides several benefits. First, it improves the performance of the secure connection. Next, privacy concerns are reduced because the end user's browser does not need to potentially contact a third-party CA to verify the certificates and reveal the browsing history. Finally, reliability is improved. If the client were unable to connect to an overburdened CA, for example, the client would otherwise accept a potentially invalid certificate or simply end the connection. And the last concept is pinning. Certificate pinning extends beyond certificate validation, right? To thwart man-in-the-middle attacks, hashes of public keys for popular web servers are built into applications such as web browsers. A similar, though it's already deprecated variation known as HTTP public key pinning, right? Let me put it here. That's HPKP, which means HTTP public key pinning. Uses public key pins, which are essentially hashed values of the public key communicated to the browser client from the server in the HTTP header. Now, after obtaining the server certificate, the client verified the public key against the hash of the public key. Okay, that's the end of the lesson. In this lesson, we spoke about the different PKI components. Thank you very much.